G'day everybody, this lesson is part 2 of the binomial distribution. In this lesson we'll touch on the formulas that we learned in part 1 about calculating probabilities with this distribution. We'll solve some problems about discrete probabilities with the binomial distribution. We're going to do quite a lot of work with our CAS calculator and looking at the functions that are offered on that calculator with regards to these types of problems. And we're going to visit standard deviation again and work with some problems that involve standard deviation. So just to recap on binomial probabilities and also discrete distributions, we're going to work through this problem. If I toss a coin 5 times, what's the probability of exactly 3 heads? Because it's a discrete variable, what would the entire distribution table be for this? What would that look like? And then finally we'll calculate 3 probabilities. 3 heads, the probability of more than 3 heads, or 3 heads or less. If you'd like, it'd be a good idea to pause the video and see what you can do with these questions, and when you're ready, start the video and I'll show you the solutions. So here I've calculated the probability of exactly 3 heads when I toss a coin 5 times. I think it's a good idea to always start by defining the variable, particularly if you recognise the distribution. So I'm using the variable x, I'm recognising that it's binomial, defining it with its values of n and its value of p. We're looking at the probability that we get exactly 3 heads, and so I'm using the formula that we went through in part 1. Our coefficient, ncx, or using 5c3 in this particular case, p to the power of 3, q to the power of 2, and 3 plus 2 gives us our total number of trials. Our combination, our coefficient, turns out to be 10. By the time we've calculated this, it simplifies to 5/16. So that's the value for exactly 3 heads, but we can have anything from no heads up to 5 out of 5 heads. So what would that entire distribution table look like? So here I've set out the distribution table, all of the possible values of x, all of their probabilities. We can see the first one that we've calculated, but using this formula for all of the other values of x, I can one at a time calculate all of those probabilities. And this is a discrete table. It has all the properties of a discrete distribution. And we can now use this distribution to find the probabilities of more than 3 heads, or the probability of getting 3 heads or less. So you can see there's our first answer, the probability of exactly 3 heads, which was 5/16. I've used the table to give me the values I need to calculate the probability that x is greater than 3. In other words, when x is equal to 4, or when x is equal to 5, the sum of those 2 probabilities will give us 3/16. I've recognised that more than 3 heads and 3 heads or less are actually complementary. Together they make up the entire distribution. So I've chosen to use that complement to help me calculate the answer to the third probability. So the probability that x is less than or equal to 3 is 1 minus the probability that x is greater than 3, and that gives us 13/16. Alternatively, I could have simply looked at these 4 probabilities from x equals 0 up to x equals 3, and that would still give me 13/16. So that's a recap on discrete distributions and what we've learned recently about binomial probabilities. We're now going to look at the same question, or the last 3 probabilities, but this time we're going to see how our calculator could have given us the exact same answers. In our calculator, when we hit the menu button, you'll see there's a probability menu, which we haven't used before. So we're going to use that one. And there's a sub-menu for probability, and the option number 5 is all the distributions that we can use with this calculator. And there's yet another menu below that, and it's quite extensive. Once we scroll down, we can see that option A and option B are for the binomial distribution. The first one is the binomial PDF, PDF standing for probability density function. The second function uses CDF, which is for cumulative density function. And so we're about to see how we use each of those functions to give us the answers that we need. So when we calculated the probability that x would be exactly 3, or we'd get exactly 3 heads, as we can see up here in our distribution table, that's when I'm going to use the the binomial PDF function. Once I select that function, I'll get a window that pops up. It will ask me for the value of n for this distribution, which is 5, and the value of p, which is 1/2. I can choose to put in a value of x, or I can leave that blank. If I leave it blank, the calculator will give me the entire distribution. So it will output all 6 probabilities that we see in this distribution, albeit in decimal form, not a over b form fractions. If I'm not after the entire distribution but just one particular value, that's where I input the value of x. So x is equal to 3. By the time I've clicked OK, I can see this output on the calculator screen. Firstly, I'll see the function that I've used, the 3 values that I've inputted, and then the answer, which is 0.3125, which is the same as 5/16. If I'm interested in the cumulative probability, so adding probabilities together, particularly between values, so the probability that x is greater than 3, this is where we use the CDF option for the binomial distribution. So by selecting option B, again we're going to put in the value of n and the value of p. Remember, they both define the binomial variable. And because I'm interested in the values of x greater than 3, the lower bound is 4 and the upper bound is 5. So including those 2 values, they're the 2 values I use for those 2 inputs, the lower bound and the upper bound. Again, the calculator will show me which function I've used, this time the 4 values that I've inputted, and the probability, which is 0.1875. Lastly, we'll look at the probability that x is less than or equal to 3. We're now adding 4 probabilities together, but all we need to select is the lower bound, which is x equals 0, and the upper bound, which is x equals 3. And by using the CDF function again, with that lower and upper bound, we get an output of 0.8125. So that's how we use the binomial PDF function and the binomial CDF function for calculating different probabilities of the binomial distribution. The next problem that we look at in this lesson, we're going to use the standard deviation. So I just want to recap what we learned last lesson about the standard deviation. First of all, we have a formula for the mean or expected value, which is simply the values of n and p multiplied together. The variance of a binomial distribution is n times p times q. And the standard deviation is always the square root of the variance. In fact, in part 1, I think I omitted the square root. So I'm rectifying that right now. The standard deviation is the square root of n times p times q. So we're going to have a look at this problem to finish off the lesson. The problem is about a poultry farm where we have 1,000 eggs produced daily, and a statistic from this farm is that 34% of all eggs are classified as large. So with reference to the large eggs produced from this farm, we could classify that as a binomial distribution. It's discrete, albeit the value of n is very high, n is equal to 1,000. We're going to calculate three things. We're going to look at the expected number, or the mean number of large eggs produced daily. We'll calculate the variance in the number of large eggs produced, and we'll find the probability that the daily production of large eggs falls within 2 standard deviations of the mean. That is to say, the mean minus 2 standard deviations and the mean plus 2 standard deviations. First of all, I've defined the variable as being x, calling it a binomial variable, using the value of n and the value of p to fully define that binomial distribution, and we'll calculate the expected number of large eggs. Using our formula, the mean or expected number is n times p, so using those values of n and p, we find that we expect 340 large eggs to be classified, or more accurately, on average, daily we would produce 340 large eggs. Next, we're going to calculate the variance of this distribution, and so that's where we use the value of q as well, q being the complement of p. You'll see here, I've already calculated n times p, so I'm using that in my calculation. That's the first part of the formula for variance, and we just need to multiply 340 by the value of q, which is 0.66. And that gives us a variance of 224.4. So that's some idea of the measure of spread. However, we would like to use the standard deviation, not just the variance. So by finding the square root of the variance, we get a standard deviation of approximately 15 eggs, 14.98. So I'm going to use that standard deviation to find the two values, the mean take away 2 standard deviations, the mean plus 2 standard deviations, using our mean and our standard deviation. So the lower bound is 310.04 when I calculate that value. The upper bound is 369.96. And so next we're finding the probability that our daily production of large eggs falls in between those two quantities. So setting this out, the probability that x lies within 2 standard deviations of the mean means that we're interested in the probability that x is greater than 310.04, less than 369.96. But we need to remember we're working with a discrete distribution. So the first discrete number of eggs that is greater than 310.04 is 311. And the first discrete value that is less than 369.96 is 369. And it will be these two values that I use as the lower and upper bound on my calculator. So turning into the calculator and using the binomial CDF function, we've used a value of n, a value of p, and those two boundaries, and we get an output of 0.951. And so there's the probability that the number of large eggs lies somewhere in between 311 and 369, 95.1%. That concludes this lesson. We've talked about mainly how we use the calculator with the binomial distribution. If you have any questions, please write them down, complete the Google form. Thanks very much.